Ladies and gentlemen, welcome to video number 25 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in Paris in late 2017. We are now December the 9th in the year 2018, about a year later. Today we propose a synthesis of the found results in this book on long-term solar oscillations in the form of an idealized matrix of these periodicities. The contents of this video start with the data, and then we will go into interpretation of the found period doubling sequences of long-term solar oscillations, and finally look into their interrelations. The summary is that we found altogether 17 remarkable spectral peaks corresponding with oscillation lengths of each more than 15 years. We start with their discovery. When were they first postulated or detected, where and by whom? You see in this table in the blue oval that the bulk of these spectral peaks or oscillation lengths were discovered before 1960. As early as 1733, Jean-Jacques de Méran proposed the 200-year cycle in the aurora. Of course, he didn't yet know that the aurora itself was directly caused by the sun. Then we have a number of periods that were found by Fritz Wolf, who are colleagues in Switzerland in the 1870s, and the Hale cycle, of course, found by George Hale in 1923. But also in 1957, the 88-year period first detected in the sunspot record by the mathematician Granger. Then we have below in the orange oval 4 periodicities which are found by Charles Sonnet at the University of Arizona and his student Finney in 1990. And the rest of the oscillations that are detected in this work, you see here, there are only 3 to which can be assigned names of early finders or perhaps discoverers, such as Huttermans in 1971, who found these periods independently of Sonnet and after 1960. This is now a summary of these spectral peaks. There are 17 of these, only 16 are on this table. The 17th is at 102 years and cannot be assigned to any of these 3 sequences. Here you see their lengths with their error bars. So this is what is found in observations. And now we can simplify these lengths and adjust them as idealized peaks, the length of which corresponds to an exact period doubling from an estimated base length, and in the case of the irrational sequence, spacings which are powers of the mean and extreme ratio from a base which is the same as in the poloidal sequence. You remember those 2 which are identical, observed at 30.1 year plus or minus 1 year, idealized and adjusted at 30.3 years. So these are the findings that are proposed in the Fivefold Sun as a book in its part 5 and the sections dealing with the long-term oscillations longer than the Schwabe length. Now, what can possibly be a physical underpinning or perhaps also mathematical underpinning for such behavior? We have 2 series, two sequences of oscillations which obey a period doubling rule. This has given a lot of food for thought to physicists and to solar physicists. The contributions were as follows. Granger, again in 1957, first found power at exactly 88 years in the sunspot record instead of 77 or 80 years as first postulated by Wolf in the 19th century and then Rudolf Gleisberg in the mid-20th century. Without this finding of an 88-year period, there would be no ground for the postulate of a period doubling in sunspot activity variations. Then Cattaneo and his collaborators wrote a paper in which was proposed that for the sun, namely for the solar dynamo, would be valid the more general physical hypothesis that period doubling occurs in many natural phenomena and dynamical systems as an intermediary stage between purely periodic behavior and non-periodic or so-called chaotic behavior. It was Joan Feynman and her collaborator in 1990 who wrote that the 11, 22, and 88-year variations in the case of the sun form part of a period double set. What is noteworthy is that she does not mention the 44-year period because at that time in 1990 it was problematic to find any power in amplitude variations of solar activity at this length, and we saw that it remains there remains very faint evidence of this length. So without the 88-year period, there is really no ground for a postulate of a period doubling phenomenon. However, the postulated physical rule underpinning period doubling, bifurcation, is not found in the case of the sun according to the findings in the present work. Indeed, period doubling bifurcation, as found and proposed by Feigenbaum in 1979, implies a certain factor, a large factor, in the variation of the amplitude in spectral peaks as the numbers of bifurcation rise. The factor is more than 6. And it is a factor for a decrease, so that after each bifurcation, the power in the next variations is lower. This was stated by Alexander Rozmaikin and collaborators in 1992 in the case of the sun. However, in the sun, we see that the amplitude of the 88-year cycle, which again is the only ground for a postulate that there is any period doubling, it is much larger than the amplitude at the 44-year period and also at the 22-year period, at least according to the findings in this work. So it cannot confirm the phenomenon of a period doubling bifurcation. So what might be a physical or mathematical underpinning for the detected period doubling phenomenon? What about the beats? Until 1975, there was a lot of research in solar physics on the possibility that the so-called secular cycle or Gleisberg cycle might be a product of beats of oscillations between close periods. What did they mean by close periods? They meant lengths detected in spectra of solar amplitude variations, e.g. in the relative sunspot number time series, that correspond to slightly shorter and slightly longer periodicities compared to the central value or the mean value of the Schreiber cycle of about 11 years. i.e. a 10-year period beating with a 11.5 or a 12-year period if detected in such a time series. In 1975, at a meeting of the IAU, however, was proposed that this was futile and a dead end. The principle of beats in celestial mechanics is well known. You see the formula, the product of two periods divided by its subtraction yields a number which is the beat period. For instance, the synodic period of Jupiter and Saturn is the beat period of their orbital periods and is this length in years. Same principle for the computation of moon cycles and many other celestial mechanics phenomena. Do such beats predict the lengths which compose the period doubling sequences detected in this work in long-term solar oscillations? In the Fivefold Sun is used a slightly different formula for applying this principle of the beats. Instead of the product of the two close by lengths that are here below, we use here the square of the central value of the peak frequency found from observations for the Schwabe length. And we renew the numerous attempts at finding a long period with this such kind of a formula, as was performed before 1975 by many authors. What is more, the close-by periods here are the lengths of Schwabe length bins as found in part 4 of the Fivefold Sun as a book, which are then simulated to be strictly equispaced according to a certain factor versus the central value. In the case of the poloidal three-cycle oscillation sequence, we use for the spacing factor the number 2 and its roots, the square root and the roots of higher degree than 2. You see in this table the symmetrical pair of years of lengths is 8.9 for the short length and 12.6 for the long length. Cole, for example, in the early 1970s, used a similar pair of lengths with other values which he detected in a spectral analysis. Here in the Fivefold Sun, we detected the true observed period for this length bin of 9.05, which is slightly different from what is calculated here from a simulation, and the same is true for the high-end value. You see how we get these numbers. 8.9 is the central value of the Schwabe cycle, 10.615, divided by the fourth root of 2, which is 1.189. And the high-end value is the product by this root of 2. So what we get is, for starting from the approximated exactly equispaced short bin length and long bin length, we get 30.4 years, which is a coarse approximation of the 30.1 year observed spectral peak and of the 30.3 idealized spectral peak. If we now systematically compare with found values in the period doubling sequences, we see that there is a coarse correspondence between each of these values. There is not much of an outlier, but it is a very imperfect fit. Is there any better fit for the other period doubling sequence? In fact, there is. The beats are able to predict the length of this other period doubling sequence. You see here we use another number to arrive at a spacing factor. We use roots of the mean and extreme ratio, 1, 6, 1, 8, etc. With the square root of the mean and extreme ratio, we obtain 8.34 years for the short length simulation, which is extremely close to the true value found in part 4 from observations, and the same for the long length. You see they are spaced farther apart compared to the case for the poloidal period doubling sequence in the previous page, because we are now dealing with the lowermost and uppermost boundaries bins for Schwaber lengths found in part 4. So with these base values, we obtain 21.8 years for the length of the Hale cycle from the beat formula, which is realistic, and using the higher degrees of the roots of 1.618, each doubled, degree 4, 8, 16, etc., we find this sequence of beat periods, and we shall see now whether they approach the period doubling sequence found from observation. This is what was found from observations here, and this is what is predicted by the beats according to the proposed formula. So in this case there is a very good fit. It fits close to observations and also close to the idealized values, because there is also a fit between idealized values and detected peaks, which is better compared to the poloidal sequence. The question now is if this is just a math trick. Perhaps it works for any set of well-chosen values, so ad hoc values. This would be useless and would be a dead end, as perhaps is the idea of period doubling bifurcations in the Sun. But if it is not an illusion, if it is not a fallacy, then what would be the implications of the role of beats in this case? We can now briefly mention a few findings about the relations between the found oscillation sequences. We can try to predict the phase relations between the toroidal cycle and the poloidal cycle oscillations lengths. This was already discussed, introduced in video 23. And here we have a number of proposed preliminary rough epochs for antiphase between these two cycles, or in phase. Antiphase, in phase, antiphase, in phase, depending on the circumstance of an odd or even cycle. Of course, this is at odds with the accepted notion in solar physics that these two cycles are permanently in antiphase. This is not what is found here, and it remains to be confirmed. I encourage researchers to look into this matter and find, if any, where the fault is in this finding of varying phase relations between these two cyclicalities in the Sun. We can now ask ourselves what may be the drivers between these three phenomena: period doubling poloidal sequence, a period doubling toroidal sequence, and an irrational sequence of oscillations. And this will remain extremely speculative, but is food for thought and for further inquiry. In this table, you see the three sequences in which we have now put in the middle the toroidal sequence based on the Schwaber length, and on both sides we have the irrational sequence and the poloidal sequence. it is proposed that the irrational sequence may be a longitudinal sequence in terms of spherical symmetry in the Sun. So we would have a poloidal sequence based on twofold symmetry order, two poles, a latitudinal cycle of amplification of a seed field in magnetic poles here in the toroidal region of the Sun via winding of field lines through differential rotation. And we are left with conjectures as to what the longitudinal kinematic of underpinning an irrational sequence might be. And we propose, for want of a better idea, that these might be permutations of toroidal vertices or faces in the solar sphere, which would parallel somehow the north-south reversals that are part of the toroidal cycle through latitudinal amplification of the poloidal field. We can also show in this table the number of rigid rotations performed over the base cycle of the respective sequences, and the implied as a square root numbers of balls that compose, that partition the solar ball in each case, with only the toroidal latitudinal amplification cycle being based on the regular icosahedral setup of 12 outer balls. In this circular diagram is shown the poloidal cycle with 30-year base period being shared with the proposed longitudinal cycle yielding an irrational sequence of oscillation peaks, and the latitudinal cycle of amplification of the poloidal field with its phase relations compared to the seed poloidal field yielding oscillation sequences on the basis of a 30.3-year period. This is now the end of video 25. In the next video we will start investigating how the solar surface is structured. I thank you very much for your attention.